So our goal for today is to try and find out what numbers we can plug in the equation below for x to make that equation be true. In other words, what numbers can we plug in for x that make x squared plus 6x plus 9 be equal to 0? I would invite you at this point to try using the things and the tools you already have. Try using the things you know about how to solve equations to get x all by itself in this equation. So you might try things like subtracting 9 from both sides of the equation, dividing everything on both sides of the equation by 6. If you do these steps carefully, what you'll see is that you can't use those kinds of steps to get x all by itself in this equation. If you think that you've gotten x all by itself in this equation, go back and double check to make sure that you've done the steps leading to that correctly, because there's most likely a mistake somewhere along the way. We can't solve equations like this using just the tools we've learned in math so far. We need an entirely different strategy to solve this equation for x. In order to understand this strategy, we're going to have to take a little bit of a detour, but at the end of this presentation, what looks like a random detour will come together to show us how to solve an equation like this. First, we need to remind ourselves what we mean by factoring. If I asked you, what are the factors of 63? You might say, let's see, I'm trying to make a rectangle with an area of 63. What do the length and the width of that rectangle need to be? And you know that 7 times 9 is 63, so you could have a 7 by 9 rectangle. So 7 and 9 are factors of 63. If I asked you to keep factoring, you might break 9 into 3 times 3. In elementary school, you learned this as the prime factorization. That is breaking 63 down into the prime numbers that multiply together to give us 63. Similarly, if I asked you what are the factors of 2x squared, I'm asking you what are the numbers that I multiply together to get 2x squared. So you might break this up into the factors 2 and x squared, because when you multiply 2 by x squared, you get 2x squared. I could factor this further because I know that x squared can be broken down into x times x. So I could factor this into 2 times x times x. What if I asked you, what are the factors of this binomial expression? 2x squared plus 8x. A way to picture this question, using some rectangles in the area model, is like this. If I have a rectangle whose total area is 2x squared plus 8x, that's the rectangle that's shown here, what do the length and width of that rectangle have to be? Well, the width could be 2x, and the length could be x plus 4. And we see that when we use our area model of multiplication, 2x times x gives us 2x squared, and 2x times positive 4 gives us 8x. So we would say that the factors of 2x squared plus 8x are the quantity 2x and the quantity x plus 4. Because when we multiply those two things together, we do indeed get 2x squared plus 8x. We learned about the distributive property earlier in the year. So if I wanted to apply the distributive property to the expression shown here, 2x times the quantity 2x plus 1, I might draw in my little arrows here. 2x times 2x would give me 4x squared, and 2x times 1 would give me 2x. Distributing is simply a way of multiplying two quantities together. If we were to think of the area model that goes with this problem, I have a rectangle whose width is 2x and whose length is 2x plus 1, and I want to know what's the area of that whole rectangle. Factoring we can think of as going the opposite direction as distributing. You can think of it as undistributing things. Remember, factoring is all about what things do I multiply together to get a particular number. So the factors of 36 are 6 times 6. The factors of 3x are 3 times x. The factors of 6x squared are 3 times 2 times x times x. Because when I multiply 3 by 2, I get 6, and when I multiply x by x, I get x squared. So if we think about factoring as the distributive property in reverse, let's say that I start with the expression 4x squared plus 2x. I want to know what two things can I multiply together to get this expression. In other words, is there anything I can undistribute from both of these? We notice that we can undistribute. We can factor out a 2x from both terms. It's like we took the 2x and we divided it out of the first term and we divided it out of the second term. From an area model perspective, it's like I gave you a rectangle and I told you its area was 4x squared plus 2x. And I asked you, what do the length and width of that rectangle have to be? You would say that the width of it would need to be 2x and the length would need to be 2x plus 1. Factoring is simply asking, is there anything that I can undistribute? How do I get a rectangle with a given area? What do the length and width need to be? Some tips for factoring. It's helpful to break each term into its factors and then see if the terms have any factors in common. So for example, if I wanted to factor the expression 3x squared y squared plus 6xyz, it would be helpful to me to write this out, to write each of the terms in terms of its factors. So this first term, 3x squared y squared, can be rewritten as 3 times x times x times y times y. The second term can be written as 3 times 2 times x times y times z. How is it helpful writing these out the long way? Well, I notice that both terms have a 3 in them, so I can undistribute a 3 from this. Both terms have an x in them, so I can undistribute an x from these. Both terms have a y in them, so I can undistribute a y from these. So if I take those common factors, the 3, the x, and the y, and I undistribute them, I put them out front. What's left behind in the first term when I do that? Well, the 3 and the x and the y came out front. So what's left behind in the first term is an x, you can see the x here, a y, you can see the y here. Now what's left behind in the second term? Well, there's a 2 and there's a z. So you can see that I have undistributed the 3, the x, and the y. I have factored those out of both the first term and the second term. So please pause this presentation for a moment and try factoring these two expressions. In both cases, it'll help you if you identify the common factors between all the terms and then factor those out. Just a hint to you that if it appears as though you factor out, for example, in the first expression an x and there is nothing left behind, think about whether or not there's really a 1 left behind there. We'll go over the answers to these tomorrow. All right, another stop on our detour has to do with products that equal 0. So I give you an expression, x times y, and I set it equal to 0. X times y equals 0. And I want to know what numbers can I plug in for x and y to make this true? Well, either x has to be 0, because 0 times y is going to be 0, or y has to be 0, because x times 0 is 0. One or the other of those two things I'm multiplying together have to be equal to 0. We call this the zero product property, that when I multiply two numbers together and the answer is 0, one or the other of the factors has to be 0. So here's an example that looks a little bit more complicated. X plus 3 times the quantity y minus 2 equals 0. What values of x and y will make this equation true? Well, either this first chunk, the x plus 3 part, has to be equal to 0, or the y minus 2 chunk has to be equal to 0. I have two things I'm multiplying together. The first one is x plus 3, and the second one is y minus 2. One or the other of them has to be 0. I can solve these two equations independently. For x plus 3 to be 0, x would have to be negative 3. And for y minus 2 to be 0, y would have to be 2. So if x is negative 3, the original equation is true. And if y is 2, the original equation is true. There's two different ways that I can make that product be equal to 0. The only thing I've done here is I've replaced the y with an x. So I have this product, the quantity x plus 3 times the quantity x minus 3, and multiplying those two quantities together is equal to 0. So either x plus 3 has to be 0, in which case x would have to be negative 3, or x minus 3 would have to be 0. In that case, x would have to be 3. So those are my two solutions to the original equation. If I plug in a negative 3 for x, that makes the equation be equal to 0. And if I plug in a positive 3 for x, that makes the equation be equal to 0. So, if I gave you a problem like this, 2x squared plus 8x equals 0, how could we find the solutions to this? Well, the first thing we would need to do is to factor out any common factors between these two terms. I notice that both terms have 2 as a factor and both terms have x as a factor. So when I factor out 2x, I get 2 times x times the quantity x plus 4 equals 0. Now I have some numbers multiplied together and the answer is 0. One or the other of these numbers has to be 0. Step 2 is to use that 0 product property to figure out what values of x make the chunks of this be 0. So either 2x equals 0, in which case x itself would just have to be 0, or x plus 4 has to be 0. So the solution is either x equals 0 or x equals negative 4. I invite you to try plugging both 0 and negative 4 into the original equation above, 2x squared plus 8x equals 0, and verify for yourself that both 0 and negative 4 are solutions to the equations shown above. Let's practice using this strategy to solve another equation. 3k squared equals 6k. So step 1 is we're going to rearrange these terms so that we have an equation that's equal to 0. Why are we doing this? Well, we want one side of our equation to be equal to 0 so that we can use that 0 product property as part of our solving process. So I'm just going to subtract 6k from both sides. So I get 3k squared minus 6k equals 0. Next, I'm going to look at the stuff on the left-hand side of the equal sign and see if there are any common terms that I can factor out. Both 3 and k are factors of each of the terms above. So I factor out a 3 and a k, and what I leave behind in the first term is just a k, and in the second term is a negative 2. So I've factored the expression 3k squared minus 6k into 3k times the quantity k minus 2. Now I have the product of some things is equal to 0. One of those things must be 0 itself. So now we use the 0 product property. Either 3k has to be 0, which just means k itself would have to be 0, or k minus 2 would have to be 0, which means that k would need to be 2. Remember back at the beginning we said that our goal for today was to figure out what values of x make the expression here, x squared plus 6x plus 9 equal to 0. Here's where we're going to tie these things together. I can take the expression x squared plus 6x plus 9, and I can write it in its factored form. If I rewrite it in its factored form, it looks like this: x plus 3 times x plus 3. If you need to pause and verify for yourself that x plus 3 times x plus 3 is the same thing as x squared plus 6x plus 9, go ahead and use FOIL to double check that. All I've done is rewritten the left-hand side of the equation in a different way. It's still the same quantity, it's just shown written in its factored form. Now I have this equation, x plus 3 times x plus 3 equals 0. I have the product of two numbers, x plus 3 and x plus 3, is 0. So one or the other of them has to be 0. Either x plus 3 equals 0, or in this case, the other factor is the same, x plus 3 equals 0. So the solution to this is x equals -3. The next step, and what we'll work on in the next section, is how do you factor an expression like x squared plus 6x plus 9? How do you know that you can factor that into x plus 3 times x plus 3? This is one of the hardest sections for the year, so I'd suggest that now that you've got your notes made, go back through and listen to the whole presentation and focus on your thinking rather than your note-taking this time.